Good afternoon, everybody. I'm Metin Gürk, and I'm the Director of Center for Artificial Intelligence Research. Welcome to our Artificial Intelligence in Action, AIIA seminar series. This afternoon, we are pleased to have Dr. Huang, a postdoctoral associate at the University of Florida's Department of Health Outcomes and Biomedical Informatics, to today's seminar. Dr. Huang's research focuses on applying AI and machine learning techniques to real-world data, aiming to enhance healthcare systems and improve patient outcomes. His work covers critical areas such as disease subphenotyping, outcome prediction, and fair AI in healthcare. Today, Dr. Huang will present on the concept of health digital twins. This concept is really exciting. You probably hear about it quite a bit. I think it's a really important concept. I think we will learn from Dr. Huang about this concept. And this concept integrates multimodal patient data to create virtual models that enable personalized, predictive, and preventative care, which is all exciting. His talk will offer insights into how AI, machine learning, and real-time data are revolutionizing patient care by tailoring healthcare strategies to individual needs. Dr. Huang, it's all yours. Thank you. Welcome.
Yeah. So first, good afternoon, everyone. And first, I would like to thank Dr. Gurkan's invitation and introduction. And yeah, this is Huang. I'm a postdoctoral associate in the Department of Health Outcomes and Biomedical Informatics. My research centers around the intersection of machine learning, real data analysis, and clinical informatics. I appreciate you being here today, and I will share something about the health digital twin, a concept I believe holds transformative potential to our healthcare systems. And in today's presentation, I will begin with the definition of health digital twin, AI, machine learning, and real-world data. Then I will share you two individual studies that focus on the model developments for different healthcare applications. And these models can be integrated into a product digital twin. Then I will walk you through the workflow and the necessary techniques to create a health digital twin. And in the end, I will summarize some future direction of this topic. All right. Now, the first question is, what is a digital twin? The concept of a digital twin originated at NASA in 1960s during the Apollo mission. When Apollo 13 encountered malfunction, NASA created a living model to simulate the conditions of the spacecraft and use this information safely guide to action and back to Earth. Later in 2010, NASA's John Vickers introduced the first term digital twin to describe a virtual representation of a physical system. The original digital twin consists of three components: a physical system and its virtual counterpart, and a connection for real-time data exchange. This connection ensures that the virtual representation can keep up-to-date information of the physical system. Nowadays, the concept of digital twin has expanded into healthcare, giving rise to the health digital twin, which means a digital twin of a patient generated through the integration of patient data and real-time updates on the patient and other environmental variables. You can check the figure on the right side. There explains how a digital twin interacts with patients in the healthcare environments. So it starts by using patient's data to create a digital model. Then the digital model is used for simulation analysis that supports decision-making and treatment selection. The patients then follows the treatment and provide feedback back to the healthcare system. This process formed a positive interaction loop between the patient and the digital model to improve the patient's health care outcome and the model's performance simultaneously. So we can see that a key element in this loop is the data, which serves as the bridge between the patient and the model. So data is important. Now let's talk about the data, especially the real-world data. Every day, U.S. healthcare system generates amounts of data from the clinical notes captured in electronic health records at the hospital to the administrative billing claims submitted by the providers and captured in insurance programs and much more. Real data is used to generate real evidence to answer important questions. For example, whether certain medical products are likely to increase or decrease the probability of a specific health outcomes. By using this information, by using this evidence, patients and providers can make more informed decisions about the care and treatment. So real-world data is very important for the creation of health digital twin, as it captures the diverse and complex nature of patients' experiences. Unlike clinical trial, which often limited to conditioned environments or specific populations. Hence, real data is important, and by harnessing real-world data, digital twin can more accurately reflect the patient's real-life conditions. However, analyzing real-world data is very complicated due to the large sample size, due to the complexity of the data. The recent advancement in AI and machine learning have been proved effective in handling these challenges. For example, some studies report that these techniques can support healthcare applications like predictive medicine, like clinical decision making. And now let me show you how to integrate the AI machine learning techniques with the real data to a health digital twin. This is my sort of a digital twin engaged with the patient. We first use AI machine learning model to create digital twin models, and the data would be include patient profile, comorbidities, lab tests, medication, and some non-medical factors like environmental factors or social determinants of health. And I want to mention that this digital twin model is not a single purpose prediction model or the other machine learning model. It can provide multiple functions. Like in digital twin, we can provide the descriptive information of the patient and can tell us the disease progression status of that patient and can predict the future outcomes. More importantly, it can simulate treatment options or estimate the treatment effects. Moreover, as a healthcare tool, health digital twins also provide unbiased functionalities to everyone who needs it, thereby advancing the health equity purpose. Now, let me show you two individual studies. The first one investigates the neural networks for disease subtyping, which means that we use AI models to categorize patients into different groups according to their disease progression patterns. And then the second one, I will share how to adopt fair machine learning practice to an outcome prediction. And yeah, as I mentioned, these techniques can be a part of a health digital twin. Now, let's share the first one, identifying Alzheimer's disease progression subphenotypes via graph-based framework using EHR. Alzheimer's disease is the most common form of dementia, categorized by the irreversible decline in cognitive function. And this heterogeneous age-related neurodegenerative disorder impacts a a large amount of patients over the world, and AD, Alzheimer's disease, is not a single condition but a spectrum, often referred as Alzheimer's disease continuum. So this term describes the progression of AD, beginning with the brain changes that often go unnoticed, progressing to memory issue, and eventually leading to cognitive impairment. So the AD continuum is commonly break down into three phases: the preclinical AD, MCI due to AD, and dementia due to AD. The duration of each phase are different and very different among individuals, like due to different factors like the sex, age, genetics, information, or lifestyle, environmental factors, and much more. And moreover, the cognitive decline risk also varies in different patients. Somebody experiences rapid deterioration and others are not. So understanding the variety of progression patterns within the AD continuum is very important, as they can lead to the development of effective treatments. And use these treatments, we can enhance the quality of life for the patient and their families. So in this study, we try to create AI models to decode the progression patterns from the real-world data. And in this study, we use a cohort from One Florida Plus. One Florida Plus is a clinical research network that contains a large amount of patients, over than 20 million patient data from Florida, from Georgia, and Alabama. And we first extract a MCI cohort based on the MCI ICD code. So the patient in this cohort has at least one MCI diagnosis code, and then the age must be less than or equal to 50 years old. Then we label the 80 patient according to the ICD code as well in this cohort. You can check the statistics information of this cohort. We have 2,500 patients, and the average conversion date from the first MCI diagnosis to the first AD diagnosis is around 900 days. The mean age is 75, and 61% are female. White group is the most popular group in this cohort. Now, this is brief information of the data, and let's check the proposed framework. We call it GAPS, and the input data of this framework is longitudinal electronic health records, which means that it's the sequence of patients' historical encounter information as a visit information. Each encounter contains the demographic feature, the comorbidities, vital information like smoking status, hypertension information, and the medications. So we then use this longitudinal EHR to construct a disease progression graph. An example is shown on the right side. You can see that each node in this graph presents a single encounters, and the shape and the color differentiates the patient. So there are two distinct patients in this example. The age links two similar nodes, which means that these two encounters have similar factors or say similar clinical information. We then use graph neural networks to learn embeddings from this graph, and the learning task of these graph neural networks is to predict the AD continuum phase in the next encounter. By learning this framework, by learning these graph neural networks, we can generate representations of each encounter, and this representation encodes the clinical factors and the outcome information, which should be helpful for the follow-up analysis. Then, after we obtaining the representation of the encounters, we arrange this representation into a sequence according to the original time order of the longitudinal EHR. So in the next step, we apply time series clustering methods on this representation sequence to learn the subphenotypes. Then in the end, we also evaluate the predictability or the interpretability of these identified subphenotypes. Okay, let's check the performance. The first experiment is to identify that which graph neural networks is best for this representation learning task. We tried different graph neural networks, including MagNet, graph convolutional networks, graph attention networks, graph sage, with different settings. And we can see that GAT and MagNet and graph sage showed comparable performance, but graph sage is the best one with the setting by focal loss and dimensionality is set to be 64. So we picked graph sage as the core function, core model as our framework. Then we use time series k-mean clustering to analyze the representation sequence, and we obtained 4 progression subphenotypes. You can check the figure on the left side. On the left side, there is a KM survival curves. The x-axis is the time, which means the day from the MCI to AD. Y is the survival probability, which means the rate of AD diagnosis. So we can see there the progression timelines are very various in these 4 subphenotypes. And let's check the statistic information of these four types. We can see that the demographic distribution are very similar, and the number of patients in subphenotype 1 is much more than the others, and the individuals in subphenotype 3 shows a rapid AD progression. The transition days from the first MCI to first AD is around 800 days, but in contrast, the individual in subphenotype 4 shows a more stable and slower progression patterns. The conversion day from the initial MCI diagnosis to the first AD diagnosis, 1,073 days. Now let's focus on the subphenotype 3 for a moment. These groups is affected by multiple comorbidities linked to different body systems like nervous, like the musculoskeletal and urinary system. The unique or say distinct feature of this subphenotype is the urinary tract infection, and this finding aligns with the existing reports, which means that the individual with MCI or AD are vulnerable to the cognitive impairments due to the urinary tract infection. And this infection also often presents as delirium and would affect the development of the AD. So we can see that the progression time is very fast in this subphenotype. The average progression time from the pre-MCI to AD is 2,000 days. But moving to the subphenotype 4, this is more stable than the subphenotype 3. And we can see that the key feature here is the comorbidity in sensory organs, especially the vision. Although there are no direct evidence to show this disease are interconnected, but some research also suggests that the development of vision impairments also affects the risk of AD. However, the transition time in this subphenotype is much slower than the subphenotype 3. The average time from pre-MCI to AD is 2,600 days. Now, this information tells us that there are different progression patterns in the Alzheimer's disease if we can appropriately analyzing the real data. And we also test the predictability and the interpretability of these subphenotypes. We use a single encounter information to predict the subphenotypes what patient belongs to. This experiment is very meaningful if we can predict or say early identify the subphenotype the patient stay in. We can design some treatment options to shift the patient from the fast progression types to a slower one. Yeah. And in these experiments, we use logistic regression and XGBoost to test the basic performance of the prediction task. And we can see that XGBoost is acceptable in these 4 class classification problem. The AUC is around 0.76. We then use sharp value to decode the importance of the XGBoost model. We can see that the common factors are age groups and some neurological conditions like memory loss. But focus on the subphenotype 3. Age being larger than 79, and memory loss, the use of anti-dementia medications showed positive correlations to classify the patient into the subphenotype 3. So it would be helpful to let us understand the disease progression pattern. And to conclude, in this study, we built a framework for analyzing real-world data to decode the subtype in disease. And the result shows that we have already identified 4 progression subphenotypes, and these subphenotypes is predictable and is printable. Okay, so there is the first study, and let me change to the second one. I will share you how to use machine learning techniques for outcome prediction and how to adopt fair machine learning practice to reduce the bias in the predictive model. Now, this study is for type 2 diabetes. So it's different to the AD, and diabetes is the 8th leading cause of the deaths in the USA. And over 90% of diabetes are type 2 diabetes. Racial and ethnic minority groups, especially the individuals facing social disadvantage, is often disproportionately affected by T2D and its complications. Social determinants of health, the non-medical factors that impact health outcomes, the root cause of the type 2 diabetes disparity, and account for 80% of modifiable factors. So type 2 diabetes must be managed not only by the traditional medical care, but also we need to address the patient's unmet social needs. So it's very important to have a social risk management tool to this purpose. But the barriers and challenges limited in the current manual screening process. So is a clinical needs that we have. We should have a automatic SDOH screening tool for improve the T2D outcomes and to reduce the health disparity. What's that? Okay, and AI and machine learning techniques provide a feasible solution for creating these automatic SDOH screening tool. However, many studies that apply AI and machine learning models in clinical setting or medical domain often overlook the bias in the data. When we natively train the model in this bias data, we may have a bias model to increase the health disparity. An example come from the COMPASS, a tool used by US courts to evaluate the recidivism risk of the criminals. And an investigation found that this tool reflects racial bias, and the black men are disproportionately subject to the inaccurate prediction of reoffending. Another example comes from the AI system that used to judge beauty contests, which showed a bias against participants with dark skin. So to prevent increasing health disparity, we need to concern the bias problem, the fairness problem in creating the screening tool. So in this study, we create a machine learning pipeline to identify the increased social risk, and that can predict the hospitalization in type 2 diabetes patient. We also considered the fairness issue, and we reduce the bias in this model. Before to introduce the framework, I need to share something about the data. We extract the cohorts from UF Health Integrated Data Repository, aka the UF Health IDR. IDR is the data warehouse that contains patients' information of the UF Health, more than 1 million patients. And we select a cohort from 2015 to 2021, and a patient timeline is shown on the right side. The index date of this cohort is set as the day of the patient first record as type 2 diabetes, and we use the 3 prior years to the index date as the observation window for feature extraction. We finally got 1,600 patients that have 1 year follow-up hospitalization records. In this study, we include 2 types of SDOH, social determinants of health, including the contextual level and individual level. For the contextual level SDOH, such as the food access, the workability, and primary and safety information, we collect this information from the public data resources as an X-person data set, and we link the patient records to these metrics according to the patient's residential address, the 9-digit zip code. For the individual level SDOH, we check this feature like the education level, employment status, and alcohol use from the clinical notes of the patient using the NLP. So that's about the data, and this is the proposed pipeline called the Individual Polysocial Risk Score, and it contains 6 steps. The first one, we first address any issues of the data, like the missing value, like the imbalance label distribution. Then we test different machine learning techniques, like the attributes, like the linear model family. And we, of course, evaluate the model by different performance metrics, from the AUC to the specificity. And we use different explainable AI techniques to help us to understand the important factors of the models, including the shock value, including the causal structure learning. And we further to test the fairness of the prediction model. Once the bias is identified in the predictive model, we use different mitigation techniques to reduce the bias in this model to provide a more fair one for the final use. Okay, let's check the overall performance. You can see that we have 10,000 patients. The mean age is 58, and 58% are female. White group and black group are comparable, although white group is the most popular group in here. And you can see the results on the right figure. This is a performance of the prediction model using different set of input feature, individual level only, contextual level only, SDOH, and a combination of both. And we can see that by using information, individual level only SDOH, we can get a good model, a acceptable model. The performance is 0.71 in AURC. And by adding the contextual level SDOH together, the performance will be improved to 0.72, which is acceptable for a screening tool, but not a diagnosis tool. Okay, we then use sharp value to analyze the important feature. We can see that housing stability is the most important one, and followed by insurance type, the number of the supermarkets in the community, and the smoking status. We can see that in from the view of sharp value, contextual level SDOH are somewhat important in this model, and we then use the causal structure learning to analyze these top important features. And we can see that aggregate assault rate in the community that patient lives in is causally related to the hospitalization outcomes. And more importantly, this feature is also point to the housing stability in the middle of this figure. So this finding is consistent with what we see in the sharp value, which means that the housing stability has high correlation to the hospitalization outcomes, but it also influenced by some contextual level SDOH, like the aggregate assault rate. And in the last experiment, we test the bias, if the bias exists in these models. On the left figure, I showed the false negative rate curves between the non-Hispanic Black and white and Hispanic groups, and it's obviously that there's a bias between these three groups. The false negative rate of white people is better than the others, so we need some techniques, mitigation techniques, to reduce the bias. And the change of performance is shown on the right side. You can see that there is a we use the equality of opportunity, which is the false negative rate ratio, to evaluate the bias of this model, and we consider the matrix between 0.8 to 1.25 as statistically fair, which means the area between these two lines. And you can see the original model is outside of this area. So the equality of opportunity is larger than 1.4. After different techniques used into the model, we can reduce the performance from the equality of opportunity from 1.4 to 1 to close to 1, which means that this model is more fair than the original one between the white group and the black group. And more importantly, we observed that the disparate impact remover, which is a pre-processing mitigation techniques, holds the best performance. The AURC keep in 0.71, so we have a more fair and accurate prediction model. So in the next step, and we use this model to embed it into the healthcare system. This is the ongoing work, and we have a mirror system that is a sandbox of EPIC system used in UF Health, and we are trying to embed the PSRS model into the EPIC. So if the physician or say the social worker use the EPIC, it would show the polysocial risk score of the patient. If the polysocial risk score is larger than threshold like 80, then a BPA would be triggered to notify that this patient is at risk. So you need to inform the patient come back to the hospital. And we have also created a interactive website to help the doctor, the provider, and patients know the detailed risk of their polysocial risk score, and to pop out the top 5 important SDOH for them, and then link the relevant the programs to refer the programs to the patients. Okay, that's an ongoing project, and well, okay. So far, I have introduced you 2 individual studies that develop different AI models for different purposes in healthcare, and the underlying techniques of these frameworks are general and can be adopted for the use in different settings. For example, we are currently working on applying the polysocial risk score for the AD patient. Yeah, but it's in progress. So, but in the last section, I would like to share the workflow and of building a health digital twin. Here is my initial design of a general health digital twin framework. In this framework, we have 2 real-world data. We have 2 data workflow. The first one called static real-world data pipeline. In this component, we aim to generate the cohort data from real-world databases. For example, in my current university, we can use Huang Plus, and to extract this cohort data to generate the AI model. This process contains how to use computable phenotype to identify the precise cohorts, and then refine these cohorts based on the data completeness. As we know, not all patient data can be used to build the model, as some patients has a lot of missing data. If we use this low quality data to build a model, that will increase the model bias. So in a separate project, in a separate study, we have proposed a algorithm to filter out this lower cohort, which contains higher data completeness. So once the data is ready, we can use this data to feed into the offline AI foundation modeling to generate different AI models. And these models will be deployed onto the online digital twin service. This service contains 2 components: the backend server and a front-end UI. In backend server is used for running this series of AI models for different purposes, and it also provides the descriptive information of the patient from the original database. Then, of course, the UI is for the interactive visualization for the end user. And a key element in this framework is the data linkage. We will connect the digital twin service to the existing healthcare system, like the Epic system. The Epic can provide a file API for the real-time data exchange, which means that the patient data can be shown on the Epic, and the Epic can be passed the data into the digital twin service. And there is a bidirectional data exchange pipeline. So that enables the real health digital twin, and that is the key component of the digital twin. Okay, and here is a use case. I try to apply the health digital twin in a clinical use. As I mentioned above, the social risk is very important to the type 2 diabetes patient, and we have built up a screening tool to screen out the high-risk patient. But think about it, if we can have a more advanced tool, and this tool can simulate the SDOH-based intervention, that it would be very helpful for the patient for the treatment selection. Right? So we try to use the health digital twin for this purpose. And there is the workflow of this application. The patients allows the system to access their data, and this data linked to the SDOH and used for the health digital twin creation. Then the social care, the social workers and the patients can manipulate the health digital twin, simulate the intervention to see what happened in the future. So based on these simulation results, the providers, the patients can make more informed decision, and the detail of this health digital twin is followed by the general digital twin framework. Okay, beyond to this specific study, I have also listed the necessary techniques for creating a health digital twin. So we need real-world data. So for the data inputs, we need like algorithm to identify the subtypes. We need techniques to link these real-world data, electronic data, to some outside factors like SDOH, like environmental factors. And for the representation learning, of course, we need techniques to learn the presentation of the patient, and we need some techniques to decode the disease subtypes, and we need some techniques for the prediction modeling, especially to analyze this kind of longitudinal data to make more accurate prediction. And moreover, we need some mitigation techniques, some evaluation techniques to ensure that our models are fair, our models are good for everyone. However, there's a room to improve this health digital twin framework. For example, the current framework relies in the machine learning. Machine learning is a predictive modeling technique that learns the correlation between the inputs and the outputs. However, it falls short in addressing cause and effect question. But cause and effect question is an important question in health digital twin. So I will exploring the causal inference, especially for the individual treatment effect estimation in the next step. Besides, using different sources of data is often to improve the representation of the understanding of the patient. And in a working study, I use machine learning techniques to identify the biomarkers from retinal images and use this information to predict the onset of Alzheimer's disease. And I believe that if this works success, and if we can integrate these type of technologies, the medical image analysis technology, or say these biomarkers from these images into the health digital twin framework, we can have a more comprehensive understanding of the patient. And the final one, it would be my long-term target. Based on the success of health digital twin, we can expand the health digital twin to the concept called health digital community. Health digital community is a group of health digital twin, and we can try some population level intervention. Image that if we can simulate a policy to modify the social risk or say social environments in a specific community, and the patient lives in this community, we can observe their outcome would be better or be worse than the original status. So this type of this concept, health digital community, can advance the precision public health. And in the end, let's review the research framework provided by provided by the National Institute of Minority Health and Health Disparity. So this framework guides the NIH-funded research for the health disparity research, but it's not limited to the minority groups, but also applicable to the broader population. And the outcomes cross from individual level to community level to population level. And I believe that if we have a health digital twin and leveraging with the real world data and AI techniques, we have a great potential to enhance health outcomes across these diverse levels and significantly to improve, to refine the current healthcare system. And that's all my presentation, and thanks for your attention.
This was great. If you are joining us online, please put your questions in the chat. We'll be monitoring those.
Is Dr. had a question?
Yes.
Yes, thank you very much for your presentation. That was a great informative presentation. So regarding the second, I believe, a study, which was AD, so I noticed that you showed the SHAP values for your models. Can you back to that slide, please?
Of course. The second one or the first?
Yeah, this first SHAP values that you put.
Here?
Yes, this one. So I noticed that there are only 4 variables here that have very strong positive correlation with the condition.
Yeah.
They are age, memory loss, and what the thing that I couldn't understand is this anti-dementia drugs, because you use them as a predictor for your model.
Yeah.
And what I couldn't understand is that, for example, when a patient is diagnosed with that condition, this medication is going to be prescribed, right?
Yeah.
So I don't know how we can just interpret this one, because this is kind of like a very, it's kind of like it's playing like a target variable that you have. So can you explain this one, please?
Okay, so that's a good question. As this cohort is the MCI cohort, so every patient in this cohort should have MCI conditions. Mm-hmm. So they may have these drug uses, and if the patients have more than drug uses in this cohort, mm-hmm. it would be proof that these patients will go to the high rapid progression pattern. So that's why the use of anti-dementia drugs shows a positive mm-hmm. Correlation to this specific subtype.
Okay, thank you.
Do we have any questions from the audience, the online group? In the chat, Brittany?
Behar Turkins had a question.
Okay, Behar, if you can turn your microphone on and ask your question, please.
Thank you. I was wondering, for Alzheimer patients, did you only do subphenotyping, or did you also predict the progression of the disease or some outcomes in later stages? I may have missed that. For the Alzheimer patients, did you do the prediction or just grouping of the patients based on time series data?
Okay. That's a good question. So in EHR data, at least in the EHR data in the UF Health or on data, we don't have the severity label, severity outcomes. But in another study I'm working on is to try to decode the progression patterns in not just AD, it's ADRD. And our learning target is to predict the mortality like in 1 year. And this is kind of prediction model of the AI disease. Yeah, mm-hmm. But we are working on.
Okay, that's good. Yes.
I have a question about the subtype 3 with where there's it appeared to be a strong relationship between urinary tract infections and the progression from mild cognitive impairment to AD. I'm an implementation scientist, so I'm always looking for ways to think about what can we do to intervene to slow the progression.
Yeah, yeah.
Did I understand the interpretation correctly that UTIs are associated with a more rapid increase?
Yeah, based on the statistical result, we can see that in this subphenotype, there high prevalence of urinary tract infection, and we do some surveys, and the existing research reports that this infection is associated with the high risk of Alzheimer's disease development.
So it seems like then they would be a high risk target. So if you've got a patient coming in with recurrent UTIs, and you could easily extract that from the EHR data, then they could be a target for some sort of either better hygiene to prevent UTIs, and there are clinical management tools. You could put people on preventive antibiotics. There's a trade-off for that, but you could consider that. And do you know if that's been done, or could you do it with as the prediction, and then turn this into the urology team or the primary care team to help manage clinically and test that prediction?
Yeah, we can first identify what the subphenotype the patient belongs to, and after some simulation to see if we give some treatment to that patient and can shift the patient from this rapid progression subphenotype to a slower. Yeah.
Mm-hmm.
Because part of that subpopulation may already be treated
Right.
for urinary tract infection, and then this model can tell you what kind of trajectory they are following, right?
Right.
And then that could be a really interesting clue. But I really like the idea of going from prediction to the implementation.
And to prevention, right?
And
So
to
we want
prevention.
to slow the progression.
Yeah.
So if you can identify them early as a subphenotype
Yeah.
or risk of having this, you could. And you're a clinician. You can add
Yeah.
this.
Yes.
I had a question related to that. I was wondering if behavioral variables were inputted at all, because dehydration
Yes.
results in
Yes.
UTI, and if someone has decreased cognition, they're less likely to hydrate, which increases the risk of UTI. And related to that, also physical activity is a huge variable that impacts progression from mild cognitive impairment to Alzheimer's disease. So I was wondering if those were input at all into this.
And for this study, we don't have the behavioral input.
Okay.
Yeah. So
That's good.
we only have the demographic feature, comorbidities, and vital information.
Okay.
Yeah.
Because it is in the EHR, so I was wondering if have you thought of trying to add it into this model?
Mm-hmm. Yeah. Can the model can handle multiple models data. So we will try to include the SDOH data into this study, but actually the 148 Plus has no patient's residential information, so we cannot link the 148 to this information. But for the other database, we can do this experiment.
And I had also another question. So we use ICD-10 codes for the subphenotypes, and if you go back to a couple slides back,
The definition.
sorry, forward, wrong way, to the subphenotypes, the third one, for example. One more slide.
This one.
So for example, here you have pain in joint and pain in limb. A lot of the times those could be ICD-10 errors where people are miscoded in the EHR. So I'm just wondering, do you have a check system in place for coding mistakes related to ICD-10s?
Yeah, for this study we don't have, but the 148 they said that 148 Plus provides a high data quality, so they may check the data inputs before they integrate the data from different hospitals together.
Okay.
So yeah.
I think this is an exciting technology, but it's still in its early
Right.
stages. And then it reminds me of there is a movie called Twins. Danny DeVito and Arnold Schwarzenegger are the twins, and then the movie starts by saying that only their mothers could tell them apart. So these digital twins are, I think it's just an effort in the right direction, but
Yeah.
Don't you think?
Yeah. Right.
Okay. The other aspect is that I wonder if we should just, look at these like the AI agents. So for individuals, there could be a digital twin, but for diseases, we can have a digital twin. And then for the environment that these patients live, there could be a digital twin. So just when all of these things come together, like AI agents, then from their interactions, maybe we can understand what's going on. What do you think about that idea?
Yeah. So there are a lot of digital twins, as you mentioned. So some studies models a hospital as a digital twin, and a department in a hospital can be also a digital twin. Yeah. But here I present is the health digital twin is just for the patient.
Yeah.
But if we have more data, we can model everything as a digital twin and to see the connection between each twin to make more informed research.
Okay.
Can I have another question?
Yes.
So for that longitudinal data that you use GNN, I wondered if you have used any kind of like mixed effects models to just consider random effect. I mean, from the statistical point of view.
For this one?
Yes. Did you use any mixed effect models for this data?
I would like to say why I chose graph neural networks GNN to learn the representation is that the graph neural networks can learn the correlation between two single encounters. But the other framework like LSTM or say the sequence-to-sequence transformer also can learn the representation, but you cannot learn the cross-patients encounter information. That's why I chose the graph neural network.
I have a sort of a practical question.
Yeah, please.
Health systems use simulation labs regularly. I think our system has 20, 30 different simulation labs across the country. How could AI help inform the health system in its decision-making around patient care, workflow, et cetera? Because, I mean, this seems to me like a simulation. And this is simulation. You're creating a new model, and that's what simulation labs do. And if you don't know about simulation labs, that's fine, but I see that as a connector point, the practical application of AI for a health system decision-making toolkit or approach.
Yeah.
And you mentioned health systems in your last slide, and I think this is a really an opportunity.
I agree.
Yeah. As this example, we can also employ this digital twin, also this simulation techniques into the current system, and IT workers or say provider if they are afraid, they can log into this system and to try some simulation of the patient outcomes. Yeah, of course you can do it.
We are at the end of our allocated time. I just want to thank Dr. Huang one more time for an excellent presentation and for the lively discussion.